Here in this part of the lecture series on programming with Matlab or Octave, we are looking at two-dimensional data sets, that is matrices. In the last chapter, we had a glance at a one-dimensional vector that is shown here, where we can define a vector in this way. Now the extension to two-dimensional, but better check directly in Matlab how to program that. So the idea was pretty simple for a vector with three elements that we can get a raw vector in this way, or a vector W as a column vector by separating the elements with a semicolon. And now the extension to a two-dimensional set, basically a plane where each element contains some number. So let's do that. That's pretty much the same as for the one-dimensional. However, we just separate the different rows with a semicolon. So in this case, it's we created a matrix M with 2 rows and 4 columns. And certainly we can extend that by just adding more numbers in a third row. Okay, that's it basically. Okay, it's a bit more complicated, but a lot more powerful once you understood and know how to deal with that. Okay, before we continue, let's write a proper program again and get that done. So we start the editor. I would just like to point out a few things here. Up to now, I always said better click away these windows here, the current folder and the workspace, but have a look at that now. Especially important in this case is this workspace. It contains all the elements we just created or created beforehand, and is showing the name, the value, what is in there, and the size. That is how many elements there are. So in this section we created the vectors v and w and m. Here on the left hand side is the current folder where basically Matlab has access to at the moment, that we ignore at the moment but continue to look at the right hand side here. And a few more comments on that before we actually write the program. So you can clear all the variables. Basically start with a clear Matlab. Clear all is the command, and that is one you have to remember. So that clears all the workspace. You still can, by pressing the upper arrow button or just typing it in again, you still can create the matrix M again, and then it appears here in the workspace. That is important to know, that if you haven't deleted this M, you might run into problems. So better clear everything before you start a program. So we usually write in the program, write the clear all at the top. You might have wondered, let's clear it again, that the workspace is cleared, however not the screen. So everything is showing in the same way. That hasn't been cleared. you could clear that as well by CLC, clear screen or something is the abbreviation for that. So that makes the whole thing even better, clearer. So we start with the CLC at the top as well. Okay, right. And now we can write the program. You've already noticed sometimes it's a bit confusing in Matlab, at least in case you make the window too small, the buttons in the upper row will just disappear. So better change that sometimes, that you have at least the green button, and I would like to see in this case the Save As button. Here it is, just appears. Okay, Save As, and we just store that in under the name Proc7. Yes, it's already there, so I just override that. Proc is already open, it's telling me. Okay, we just save that into the name Proc8. Okay, so our job is here to look at the matrix and how we can deal with that. So let's do that again and continue with this stuff. Okay, I would just like to run it. There's something missing. I forgot to close the line with the bracket, and now it should run and produce this matrix. Okay, so what can we actually do with this matrix? One thing is that you can operate, just, let's say, multiply the matrix by 3. So it's an operation by element. In the same way you could, obviously, or doesn't come to anybody's surprise, that we can add or divide by a number. So that is the operation by element. So that's neat. What else would you like to do with a matrix? Certainly, as with the vector, we extracted one number, one element from it by giving it a index. The index at the moment is 3, the position is 3, and the content is 3. So that you won't confuse that, we might just write it in this way, and then it's more better to see the third element is 3. In the same way, in a similar way, we can have access to single elements in the matrix. That is, we just need to write down in the matrix the coordinates. Let's say 2 and 3 separated by a comma. When we do that, the 7 is extracted. I'll just print out the M again, that we can better spot that. So, second row, the first coordinate is the 2, third column, and the element is the 7. As for the vector, you need to remember the notation. Perhaps think of it as battleship, which you'll probably have played when you are young, or still like to play it. So you need to define the coordinates in with Battleship. It's ABC and so on. So, and a number in the other direction. And for instance, B8 would be this one. Okay, and with here, it's just a number starting from 1. It's an integer. So the definition gives M1 is the first element in the matrix M, 2, 3, second, third coordinate. And now you can extend that, and that is shown here. In the same way as for vectors, you cannot just access a single element, but a whole section, and that is written down with 2 numbers, starting and end value, in this case, separated by a double point. Let's check that out, how that works. So M two, 3, 3 would give you second and third row and still the third column. That is third column, second and third, that is 7 and 11. Right. And in the same way you could access many elements or even sub matrices by always extending this notation. What is sometimes confusing is that there are a few abbreviations or shortcuts in here. For instance, you could write down M in brackets double point comma 3. That would extract the whole column. All, the double point just means all elements. Is this double point. So you don't need to spell out 1, 2, 3 or 1 or whatever. The thing is, that is quite neat. It's not just saving a few buttons, but in cases where you don't know the size of the matrix, you can use that. Right. In the same way, or in a similar way, as for vectors, you could even change the position or swap them by going from the third in steps of -1 to the first element, in this case the row, and the third column. Okay, probably you've, at least I have forgotten what the matrix M looks like, so we just write that down again. So 3, 7, 11 is swapped the direction by this notation. So quite powerful. What else? With the vector, let's write that down again. We had, in the last chapter, we had already seen that we could write a single element into this vector. Okay, again, not surprising, we can do in the same way with the matrix. That is, at the coordinate 2, 3, the 99 is written into the matrix. So, changing elements, you always need coordinates. Right. Could we extract this one? Let's see what that gives. we get an error message because there's nothing in the matrix at the position 5, 3. It's not big enough, so it's telling us index exceeds matrix dimensions. Fine. In many cases, that's actually creating problems, but it's obvious or logical that we have problems doing that. Could we actually write at the position 5, 3 something? 10,000 at the position. What would happen then? Yes, we could. And that's a bit confusing here, how the matrix is showing up here, because the window wasn't big enough. I just make that a bit taller. The fourth column is separated, showing up underneath. So I just repeat that, and then it's big enough. Anyway, the M53 is 10,000. So that is this elements, and all the other missing elements are filled automatically with a 0. So keep that in mind. You can increase a matrix, and everything where you haven't defined what the element is set to 0. Right. Let's see whether I've forgotten something. Yes, there's one thing which is very powerful in Matlab. Once you have got a matrix, let's say this matrix M again, let's just have a look at that again, and create another matrix M plus 3. Okay, matrix M and N. And now you can even multiply different matrices with, in case they have the same size. And that means dot multiplication means element by element of each of the matrix M by element of N. So that gives a new matrix P with the same size, and where each element is calculated from the other two elements of matrix M and N. There are a few other things which are neat when operating with matrices. For instance, you could easily calculate the sinus of each element. That would just give a new matrix P with the same size, and that is, size means same number of elements, and the sinus of each element calculated. Actually, I forgot or should mention now what this size looks like. When asking how many elements just there are in a matrix, so just press size and the matrix in brackets, and you get in this case two numbers, 5 rows and 4 columns. So 2 numbers, and that is quite helpful to check what the how many elements there are. From the vector, we already had the command length. If we would apply that on the matrix, it gives the larger value of these 2 values. That is, in this case, 5. But usually you would take the size. Okay, what else is missing? One thing, for instance, you would like to calculate the sum of the matrix M. That gives actually 4 numbers, and that is the sum for each column. Try that out. Again, as it's quite useful, check in these cases how the sum is used by pressing help sum, and the help is telling you that it's the sum and gives some hints how to use that. For instance, here it's telling you that you can actually change the dimension where to calculate the sum from. That is, in the matrix when summing up with this comma 2, you will get the sum for each line, for each row. Quite strong, powerful, and useful. And there are many other commands in Matlab which operate on a matrix. For instance, you could calculate the mean value of M, or the standard deviation of these matrix, and then you get the mean or the standard deviation for each column as for the sum. So that's quite neat and really helpful. Okay, just check here again. We already scribbled a few lines, so a number of variables were created and appear here in this workspace with all the size. Right, make sure whenever you work with matrices that you don't confuse the column and row coordinates. Actually, I quite often get confused and need to check, and that you know or have in your mind the size of the matrix. I just check whether I've forgotten anything. Okay, matrix, looking from the more mathematical perspective, means linear algebra, and there are a few things which are helpful. For instance, you can calculate the transpose of a matrix by just typing in transpose, or here with this little sign up there, swapping, basically creating the mirror of this matrix with the symmetry axis being this diagonal line. It only works for square matrices. The inverse you can calculate, and similar thing. So if you need to know that, look it up. Perhaps just check help inf and it will tell you what to do. Okay, let me just check whether I've forgotten anything. Yes, here is the spoiler. And what is really neat and helpful, and in the future exercises we'll look at that, and hopefully you will make use of that in real work. You can easily display the matrix. So having this matrix here, you can think of it as an image with some numbers. So you can just display that by typing image sc, that scales the matrix M, and you get a new window popping up. It's actually this one here with the values in there showing up in colors. To create a color bar, you just press color bar, and that is showing up here So it's the yellow is the higher value, and the problem here is just we had this value m with the coordinate 5, 3 being 10,000, so it confuses the whole thing a bit. We just change that to a smaller value, being 5, and let's change this value, the 99, to a smaller value as well, to 9. And now we would like to display that. And now we can actually see that all the colors appear, and you can read off the graph of the color the value. So that is the first step towards thinking of a surface with basically a two-dimensional mesh with data as an image. Actually, for instance, for your images from a camera, usually you have 3 colors, RGB, and that would mean having a 3-dimensional data set with intensities for the different colors and a 2-dimensional image. So that would be the natural extension to 3 dimensions. So we look at that in an exercise later on in this series. Okay, that's enough for now. See you soon.